Welcome, everybody, to Stay Curious. I'm your host, Mark Marquette, broadcasting live like we do Monday through Friday from the studios in the American Space Museum in downtown Titusville. And we are happy to welcome back to our program Kevin Hoshstrasser. Kevin?
Thank you. Thanks for the invitation.
Well, great to see you. Kevin did a program on the SSMEs a little over a year ago, quite popular. So we know that the F-1 engine piques a lot of our Stay Curious watchers today, literally from all over the world. So if you've got a question for Kevin about something about the F-1, give us a few minutes into the program here as he's going to answer a lot of things. And Kevin, you said you've got the story of F-1 that I've never heard and our watchers have probably never heard.
Yeah, that's one of the more interesting things that I can bring to this, besides this big monster model.
Look at this gorgeous 3D printed model you have there. You're going to go over that in detail with us.
Well, yeah, I will. But first, the one thing is, you already had a couple F1s. It looks like models in your display case out here. But what I saw was you have a 1:18 scale F1, and I don't know if my wife, she made her career. She made her career out of trying to take complex Space Center topics and breaking it down so it's easy to understand for the public and the press.
That's right.
So
Lisa Malone, your beautiful wife, she worked for Hugh Harris.
So what I did was, as you know, I made the SSME model 12:1 scale, and then I made a 1:18 scale F1, and they're identical size.
Yes, they are.
And so I'm always bragging about the F1, a Rocketdyne product. And my wife would say, well, to really tell the story, it looks like it's the same size. She understands scale, but the general public might not understand that this engine is so much bigger. So as a favor and a dedication to my wife, I made a 1:12. So when you put the 1:18 next to it, or the SSME 1:12 next to it, you can see really how much bigger this engine is.
We should go get that, Marty, if you got a chance to get that. I took a picture. Kevin donated an SSME and a F1s right out the door here, Marty.
Yeah, so bring the SSME out to the 1:12 scale so you can see the difference and see how much bigger this is.
And I took pictures, but I didn't get them downloaded in time. As usual, I had some people need my attention here at the museum. But Kevin, tell us a little bit about where you grew up. How did you become a rocket scientist?
Well, I grew up in Dayton, Ohio.
Dayton, Ohio.
Yeah, and working.
I grew up in Finley.
Yeah,
Way up 75, about 2 hours.
Well, and my father was he was good at trying to get us enthused in science and going to college, and so even as children, he would get us up and we watched the Apollo or the Gemini missions and some of the early ones, and get up in the morning because they always launched at 7 o'clock in the morning.
Yeah, right.
And so I was always enthused, and I was in elementary or junior high school when Apollo 11 went up, and so of course that piqued my interest.
Here, Marty, we can make room over here in front of our set here at our Stay Curious set. There we go. Put the American flag over here a little bit. There, you got some room there.
You can see how much bigger this
Get my
F1
Buc-ee's
engine.
breath mints out of here. You got to go to Buc-ee's. You've been up in Buc-ee's in Daytona, haven't you? Yeah. All right.
But this really tells the story about how much bigger this F1 engine is compared to an SSME, and the SSME is not a small engine. This is a pretty big engine. So we'll see it here in a minute. But
and what we have behind us on our green screen, I'm sure some people have been wanting to know what that is.
Stop.
Okay. This engine here we're looking at on our green screen.
yeah, so what we're looking at there, that's a museum piece that was down. As you notice, it's missing the nozzle extension, the part that's below that big volute.
Yeah.
And it's also, but the reason why I brought this picture that I had is because if you notice the high pressure fuel duct, on my model here, the high pressure fuel duct is straight. It's straight, but you see on that one, it's U-shaped. And that's just an example of the different changes that have occurred to the F1 over the years.
I see the U in the middle there. Okay.
And it started out, there was several different designs and different configurations of this engine. The first, they would do different ways. They would want to support these ducts. They initially started off as internally tied, which meant they had internal tie rods to keep it rigid. and it was on the inside. Then they moved those to the outside, and then they went to the U shape to avoid a water hammer. And then they determined it really doesn't need a water hammer protection for it. And they also wanted to do more to strengthen the connection between the pump pack, the pump package right here off the side, and the structure of the thrust chamber. And you can see you can see it. They've got these tripods that secure it, and they also made these ducts extremely rigid. So these high pressure ducts, usually which don't support too much structure, they just carry the propellant. This one actually uses it to stiffen the connection between this rotating pump package.
To act like a brace.
And so,
in there.
and so that's the final. This is the final configuration that we flew on the Apollo programs.
Well, we're going to get more into that. I was interrupted you there about how did you become?
Oh, okay.
Where'd you go to college and to learn all this?
What I did was, I think I told you I kind of ran away from home from Dayton, Ohio, and moved to Orlando in the mid '70s before I finished high school, and came over and actually saw the Saturn 1B launch, the Skylab missions. And of course, they weren't the Saturn V, but at the time I didn't know the difference. I was just excited. And actually, I would come out here just to Titusville, not far from here, and sit on the seawall and watched it. And as soon
in front of J.C. Penney's,
and as soon as it cleared, I'd get back in my Volkswagen and drive back over to Orlando. And so that's really what hooked me. And then I went back to Dayton and started college there, and then decided I want to go back to Florida, and transferred down here to UCF. At the time, it was called FTU, but went to and finished working part-time or working full-time and going to school part-time. And I took the long way through college and graduated just after STS-1. So I missed STS-1, but I was able to join the program at STS-2. But the bad news is I couldn't get the job here at KSC. I was hired here at KSC and transferred and to open up the Vandenberg offices for Rockwell Space Division. Worked a couple years at Space Division and transferred to Rocketdyne. And then supported Rocketdyne. Of course, we didn't launch many from Vandenberg Air Force Base, as you know.
Right.
But what we did was we were always on the move. When you're at Vandenberg, you have to support the launch site for tests. You have to go to Canoga Park, which was the main headquarters where these engines were manufactured. And of course, we had an operation at Marshall Space Flight Center, and we had the SAIL, this Shuttle Avionics Integration Lab at Houston, and the Stennis Space Center. At the time, it was called NSTL, National Space Technology Lab, where we'd hot fire the engines. So that's what my career was, just moving around a lot. And when we had spare time, we'd get Vandenberg ready for a launch, which never occurred. So what happened was during the Challenger...
For a shuttle launch, it's like 6.
Yeah. So what I would do is when the Air Force decided during the Challenger downtime that they did not want to go with the shuttle launch anymore, I was transferred to Florida. I had my choice to go into Canoga Park or to Huntsville or to SAIL in Houston. But I had spent so much time down here in Florida, and that's where I met people like Marty and all the other folks. I would come down, and my job typically was third shift console operator for SSME. And that's always, I did the 7 to 7 shift, and that was what I usually got stuck doing. I just stayed with the program, worked my way up, became a manager of safety and quality, then became a chief engineer by then Boeing had purchased Rocketdyne, and I moved into the Boeing corporate world and became the chief engineer for the launch site for Boeing and all its contracts. And then we sold Rocketdyne, and that's when all my friends changed their badges. And I stayed with Boeing through the end of the program. I became the program manager for Florida Space Shuttle Operations, what we call FSSO. And then after a couple of years of that, I was also named the senior site executive for Florida Operations when my boss, Bruce Melick, retired. If you know Bruce.
Former Coast Guard astronaut.
Yeah. And so I stayed with the program until they threw me out at the end of STS-135.
They threw a bunch of them out. They threw Marty out, you out. We understand that. What a fascinating resume there, Kevin. And this is the quality of people that we love bringing on Stay Curious. Who live here on the coast. I see a lot of people excited about hearing about the engine. I've got some notes here. I want to ask you some questions. Uh,
Well, I can answer
uh,
them maybe right off the bat. Let's go
Keith
through
Sewell there says hi to us. He's in Arkansas.
it. Uh-huh.
Tom Usiak's watching. We got Dave Stangy's up in Michigan. Looking forward to spending the next hour with you all and hearing all the latest news. We've got Ophelia in France watching today. Bonjour.
Bonjour.
Yeah.
Bonjour.
Tom Celentano, he watches the show every day. He's up in Connecticut.
Mm-hmm.
Ralph Palmer, 1967, greetings from Australia. Always love watching and hearing about engines. And Mark Thel, we've got a whole group of people that watch this. Carlton Bailey,
I know
Man
that name.
Space, and which is Mitch Rothman, and Steve Jokums, one of my customers. Father Joseph Kokrak worked at Rocketdyne in Canoga Park on the F-1.
Oh, really?
Kokrak. Built a model for Joe when he was fighting cancer, and it made his day.
Well, I'm going to encourage him to take part because he'll probably know some of the names that I bring up that gave me the experience in the F1.
He may have passed away.
Oh.
But anyway, fighting cancer, he said.
Oh, okay.
Can't think or hear the word Rocketdyne without thinking of the great Lee Solid.
And he's one of the names I was going to bring up too. In fact, Lee had passed since the last time we met each other in this forum.
Yes.
And he was one of my mentors.
He was a business mentor of mine here. I got to know him very well, and hope his family's doing well and his wife and all. But this is a man that just how do you characterize Lee Solid?
Well, let me go out of order for my presentation. When I first joined Rocketdyne, everyone I worked with, all my mentors, a lot of my coworkers were F1 experienced engineers, and Lee Solid was one of them, and a fellow named Dick Carlson, that Marty knows.
Yeah.
He was the resident expert in the floor, and whenever we had a big problem, we'd call Dick, and so he retired sometime in the early 90s, I think, and he had all the F1 instrumentation, all the F1 data. And so he was cleaning out his office, and we were wishing him, good luck in retirement. And he gave me his F1 documents. And so this is what we call F1 IPB, which comes in handy. This is a document that Rocketdyne produced to tell you how to build an F1.
Illustrated Parts Breakdown.
IPB. And as you can see, it just has pictures of what it takes and what bolt numbers. And anyone who worked at Rocketdyne will recognize an IPB.
Oh my gosh.
And it shows the details of how to actually assemble an F1 engine. Well, I had this over the years, and so early in retirement, I kept in touch with Lee, and we would always run into each other at all the events. And he said, Lee Solid was actually contacted by Jeff Bezos. Remember when Jeff Bezos decided he wanted to pull some F1 engines off the ocean floor because he had too much time and too much money, and he could afford to do that. It was a great accomplishment.
Yes,
and he actually asked Lee Solid to be his technical expert.
Oh, really?
To do that. So the first thing Lee Solid did, he came to me and he said, Kevin, I understand you have Dick Carlson's old document. So I burned a copy of this document, and Lee used this document to go ahead and identify all the parts as they came in the port that Mr. Bezos's team had dredged up and salvaged. So he used it to great extent. I never got it back because it was so trashed.
Oh.
But so Lee played a big role in that. And with this document, and Lee's firsthand knowledge of the F1, he was able to identify which part belonged to where. And if there's any question, this document came in.
You'll see a few of those parts here at the end of the show here. Another question I have, did you use the Marshall test stands that were torn down this week?
No, I've never seen a test stand. The test stands at Marshall were pretty much inactive. When even for SSMEs, they stopped that early. Now, that's a separate story. When they first started testing these engines, they started testing them at Santa Susana, which is a suburb of Los Angeles. And if you can imagine the rumble from one of these engines in the Los Angeles area, it would shake and rattle the dishes and the windows. And they also tested some of these at Marshall. And so the folks at Huntsville also had some broken dishes and windows from all the rumbling. And what they did was, of course, they tried to put a public affairs spin on it. And what they would do is they would tell the local community through their outreach that what you were hearing was the sound of freedom. And that was typically in the middle of, it was early in the Cold War, and people thought, well, it was national security, and so they tolerated it to some extent, the rumblings and the broken windows and the things that would go on. But over time, they decided it was time to get out of Santa Susana, and the Marshall also shut down their testing, and that's when they moved all the testing to the NSTL, the National Space Test Laboratory, which was renamed after Senator Stennis by President Reagan back in '88, I think, and now it's called the Stennis Space Center there in Picayune, Mississippi. So that's where they tested these. They also did early tests on these at Edwards Air Force Base, where of course you don't have to worry about anything for hundreds of miles from that
Yeah.
location. But let me go over just a quick
note there. Somebody's maybe sorry we misspelled your name. Doesn't have O-E-R. It's E-R on the end. I meant to check that, Marty. Sorry about that.
It kind of makes it look Dutch, doesn't it?
But yes, Duck. But it is German, and it means
High Street.
High Street.
Yes.
High Street. Okay, High Street.
Well, this is the most powerful engine ever made. Even to this day, this F-1 engine is the most powerful engine ever made. It was rated for the Apollo program at 1.5 million pounds of thrust. But after the program was over, they did some minor work. They had several of these left over, and they were thinking about trying to see if anyone else wanted to use one, if we get another program started using this monster engine because of its high reliability and its high power. And changing the thrust, the mixture ratio, and some of the components, they were able to tweak out 1.7 million pounds of thrust out of this engine. And it is rated now in the history books as a 1.7, even though it was a 1.5 during the Apollo program.
Very interesting. We're going to look at some legacy pictures here,
Okay.
and then get to your charts there that we talked about there, because I know you're all fascinated about this space history. We're coming up on 55 years ago, January 31st, that Apollo 14 was launched to the moon, which I think is an underrated return to flight mission, with Alan Shepard leading two rookies, basically three rookies there. I love this picture. This is one of my favorite pictures there. That's Apollo 15 rollout. Okay. If there was a black band right here below above the slaw in the CM, this would be the famous F500 dummy that was took out for a fit check. But that is 15. Launch of 15. I told Kevin earlier, I said, I can't say Saturn V without saying the mighty Saturn V. Okay. And sorry, mispronounced. There's no O-E-R, it's E-R on the end.
Everybody misspells it.
Apologize for that. And many of you have been in this very setting here at the Kennedy Space Center's Saturn V Center, where you take a beautiful bus trip out there. I know many of you walked this lane there with all the Apollo patches, and then looked up at the tremendous the size of the behemoth is incredible. Of course, over a football field in length, and everybody's going to the rear end there when you go through the talk. You come out there, and the first thing you see is the engines, and then the cameras start coming out there, the business end of the thing. And just to give you, those of you who've not been there, it is gigantic. In fact, there's Carlton Bailey. Time I went out there with you, CB, taking a picture of those engines there. Just fun to watch people walk out of the presentation, and there they are. And as a photographer and an artiste, I've always looked at different ways to get those engines, to look like you're not in there. But one amazing, the cluster of four of them worked great together, and just like the great SSME engines, there was never a catastrophic failure of the engine during a flight. A couple times they had to shut one down. I know that in the following the shuttle era to the first launch, I think people really thought those turbines would let loose somehow and take out the back end of the shuttle. That never ever happened with 135 launches. So, and Lee Solid always bragged about them being the greatest engine ever made. And then he said, then we trumped it with the SSME. So, Kevin, I'm turning it over to you now, my friend.
Well, like I said, this is a piece of history here. I think that you showed one of those charts that showed the dimensions of this thing. It was 12 feet in diameter and 18 and a half feet tall. So this is a pretty big engine. It's still the biggest thing out there. It ran on two propellants, RP1, which we typically call kerosene, and LOX. Um, and I know that you know what one of the big measures we have for engines is called the impulse, or ISP. Now, the impulse or ISP for this engine was kind of low, 265 seconds. When you compare that to the Rocketdyne SSME, that was 452 seconds, which meant it was more efficient. ISP is the number of pounds of propellant divided by the thrust per second. So it
Okay.
tells you how efficiently what you're getting per pound of thrust, per
Per
pound of propellant
second.
per second. And so the
Okay.
ISP is pretty low, but it doesn't compare. But at the time, that was about the going rate for ISP. Um, this engine, though, the five of these engines, drained that tank, that first stage tank, in two and a half minutes, 150 seconds. It drained 4.4 million pounds of propellant. That's how big this pump is. There were five of them, but that emptied
How
that
many
thing.
swimming pools?
It depends on how big your swimming pool
Yeah,
is, but
sure.
4.4 million
Your pool, not
pounds.
Marty's.
Yeah, yeah.
Marty's is
So the state, what we called stage one for the Apollo program, was 2.5 minutes, and then of course stage one fell away as the F-1 engines did with it. Um, the uh, like I said, the RSP really doesn't compare to the modern ones. But uh, let's see what I was thinking. I was thinking about something else, but
the RSP as they were draining the talk to you about
oh,
how many swimming pools
this left
so many
the first
gallons.
stage 38 miles up and traveling 5,500 miles an hour. That's what I was going to say.
38 miles. Okay, the first stage on today's Falcon 9 is about 20 miles, and some of the others.
So this goes up pretty high.
Uh-huh.
So it gives it a good head start. Gives a good head start. So what I really want to talk about today was the story behind the F-1, and not many people have heard this. When I first joined Rocketdyne, I worked with a lot of F-1 experts and people who actually designed it and operated it. But there was one gentleman besides Lee Solid, who I worked with a lot, who was an F-1 expert, was a guy named Vince Wheelock. He was stationed at Canoga Park, and he was in charge of all field engineers. And he was actually the man who hired me. And so over the years, every time I found myself in Canoga Park, of course, I'd swing by Vince's office. He was one of my many bosses. You always have one boss. And I would swing by and say hello to him. And he would want to know what's going on at KSC and what we were doing, and we would exchange stories. And he was eager to hear, my current events, and I was always to hear his stories. Well, when I was in quality, I had a manager who would take every July and go try to find a new Major League Baseball stadium. He wanted to be in every Major League Baseball stadium. You might remember him, J.J. DiGiovanni.
Oh, I thought you meant Merle Jack.
No. It was my quality manager. So he would go on vacation, and so I would fly out to Canoga Park and act on his behalf for 2 weeks. And of course, when you're acting in that role as director of engineering for the Canoga Park for SSME, you don't want to do a lot of changes. You're not there to.
Right.
You just want to keep the train on the track. And of course, 2 weeks is a long time. I missed my wife, my family, but I would always hang out at the plant. And so what I would do is at lunchtime, I'd talk to Vince's secretary and find out when he's going to lunch. And I'd accidentally run into him in the cafeteria. And I would get in line behind him and get the same food he got because I knew he always took it back to his desk. So I would go back to his desk and I would just ask him questions. And he told me the story, not only the F-1, but of the nuclear engine and the Aerospike engine and the early days of the Pratt Whitney Rocketdyne competition we always had going on. So I learned a lot of this from Vince Wheelock and verified it a lot with Lee Solid, who was the one person who helped me a lot. This is the story behind the engine. In 1955, Rocketdyne had an internal R&D group of very smart people. They were set aside. They were given money to do fun stuff. And it was the advanced design group, and there was an experimental development group that would make hardware differently to see how they can make different hardware. When 55, they took the group together because they were always fighting. They'd get a contract for things like the Snark or the Navajo at the time, those little engines. And of course, they were still working with the offshoots of the V2 engine, trying to get that to work, called the A7, we called it. And they would always get a request to say, okay, we want a 150,000 pound engine, or at the time, the highest we made was 275,000 pound engine, the Navajo. And what would happen is you'd get the contract, and then the customers always come back and say, well, the payload, which was typically nuclear weapon, because that's what we did in those days, or in mid 50s, that's what they were used for. They'd say, well, we need 10% more thrust. So all the engineers have to go back to the design and get 10 more. And then you get further on and they'd come back and say, you got to shave 500 pounds off your design because the growth of the other things. And so there's always this, they got in this rut where they'd always be doing this. And they got tired of it. So these two advanced groups got together and they sat down in a room, and the leader said, I want everybody to think, what is the biggest engine we will ever need? He said, don't think about the purpose of it or how far in the future. What is the biggest single engine that we will ever need to design? And you don't need to defend it too much, but tell us. So he went around the room, and at the time, the von Braun people had already said that the biggest engine they think they'll ever need is a 400,000 pound engine. It was just someone's opinion in von Braun's group, but everyone kind of aimed at that. They said, well, what's the other one? So people would throw out different numbers, and one person threw out a number of 1 million pounds of thrust for one engine. And in those days at Rocketdyne, we had this saying, we called it a BHAG, big, hairy, audacious goal.
Big, hairy, audacious
And that's what
goal.
when we really wanted to stretch something, we called it a BHAG. Well, someone in the room did a BHAG and said 1 million pounds of thrust. But people say, what in the world would, that's science fiction. You never need it. But they said, no, it's a fair question, because we want to know what the limits of what's the biggest engine we can build. So what they said was, let's take some internal R&D money and let's try to do the preliminary design to see what's the limiting factor. What's going to tell us the nozzle problems, the turbines, the pumps, what was, the heat, would it blow apart? What's the limiting factor? So they spent a couple of years doing that, internal money. And they came to the conclusion that there was no limiting factor at 1 million pounds. They could build it. You had to take things and make them very big, and you had to use a big first stage. And of course, you have to remember, this is 1955. And so, that was a big, hairy, audacious goal. And so they took it to the Air Force and they said, we were playing around. And
I knew there.
We played around, and we'd like to get some funding. And the Air Force said, go design it. So we took a small contract of just, a very small amount of money coming through to keep the IR&D people busy. And they roughed out a preliminary design for a 1 million pound engine. And they came to the conclusion after even more research that there was no limiting factor to a 1 million pound engine. You have to remember at the time, though, this is 1955 to 57. So in 57, the Air Force and DARPA at the time came back and they said,
DARPA, tell everybody what.
Yeah, the DARPA they were helping all the branches.
Defense.
Advanced Project. DARPA.
Right.
We'll ask one of the viewers to look that up for us. I forget what DARPA stands for.
Department of Defense program, yes. DARPA.
Defense Advanced Research Projects Agency.
There you go.
DARPA. So anyway, so they gave a better funding contract to say, do some detailed design. And so what Rocketdyne did was with the money they had, they built an uncooled thrust chamber, which meant you really couldn't do any testing more than a couple of seconds. Just to start, you could get it almost in the main stage, but you could get the engine thrust up. And of course, they hodgepodged all the other components, but the thrust chamber was something that we worried about as the limiting factor. And that went smoothly, and there was no problem. They understood there was going to be a rough start, and they saw a little, instability in the engine. But what they did was they roughed it out, and they were testing that in 1 to 2 second increments. And they did that for a number of years. And everything was working fine. They said there are no limiting factors. We could build a 1 million pound thrust engine. And so in 58, NASA became an entity. In October 1st of 1958, NASA was created. And the first RFP that went out from NASA NASA, was the RFP for a 1.5 million pound thrust engine. And everyone sat around, and Vince Wheelock was telling me they were dumbfounded. They said, we thought 1 million was a BHAG. It was just way bigger than anyone could imagine. It was science fiction. But here NASA put out a 1.5 RFP. In those days, RFPs were running a little bit different. The RFP went out 3 weeks, the third week in October, and the contract was awarded to Rocketdyne around the first week of January the next year. So if you can imagine how quick an RFP was put together, and a proposal put together, and a proposal accepted and funded. And so everyone thought
3 months.
yeah, but everyone sat around there and thought, why did they pick 1.5 million? And everyone was looking back on it saying, someone knew something, because that's what the requirement turned out to be for the Apollo program. And so no one can really answer the question, but NASA put that out, and that's how we came to a 1.5 million pound thrust engine that quickly in 57. And development started. They started detail and design, actually making hardware, and trying this and taking the test stands and trying things out. And they actually put it together. And in 1959, they actually got to 1 million pounds of thrust, the first step, 1 million pounds of thrust in the 58 timeframe. In 59, they got to 1.5 million. Now, you have to remember that Alan Shepard didn't launch till 62, right? May 1st, 62, or May 5th, 62. He launched on a 75,000 pound engine.
61, actually.
It was a 61?
Yeah.
I'm sorry.
Yeah.
His rocket, the Redstone, was a 75,000 pound engine. But Rocketdyne, at that very time, was testing successfully full duration 1.5 million pound thrust engines. So you talk about science fiction. And at that time, we did not know what was going to be needed for the Apollo. We didn't even know what the Apollo program was going to be. So that tells you, someone knew something that far in advance. And there are some real smart people out there developing this.
Absolutely. And we got some smart people watching it today. Steve Jokums, thank you for watching. My daughter Jessica's watching, getting some rocket knowledge there up in Tennessee. Jim McDade, he lives in Huntsville. He's on a lot of social media and knows what he's talking about. He says, wonderful show today.
I wonder if he remembers any engine testing at Marshall. Broken windows.
He said it holds the record for the most powerful single chamber liquid engine on there, and perfect record on the thing on there. Let's look here at a couple fun sort of pictures there. I mean, that you just feel how big that is in the picture there. The rollout, of course, 1.5 million pounds of thrust times 5 is 7.5 million pounds. And that was incredible. Somebody asked about the Starship first stage there, the big rocket that they're using there with 30-some engines.
That'll be a large thrust, but it'll be 30 engines. We're talking about just the performance of a single engine. But
what's the advantage of a cluster of dozens of engines versus 5?
Well, the way it's evolved, it doesn't look like there was much of a difference. But early on, when we would cluster fire engines, we did see very isolated, but we saw some real thrust interference between engines. Sometimes, if it wasn't, we had ignition problems. Sometimes one engine close to another engine would snuff it out. And so there was thrust interference, and the two had to work in conjunction. They couldn't interfere with each other. And so thrust or clusters were kind of something you worried about, and you wouldn't fly a vehicle until you did a full-up cluster firing of it.
Mm-hmm.
But yeah, right now you can see it with the Falcon 9. When the Falcon 9 first came on board, a bunch of us Rocketdyners kind of scratched their heads and said, I wonder if they're going to have thrust interference problems. And evidently they never have. And they have, 33 engines on the south end of the Starship, and they don't appear to have any thrust interference problems, which...
is that the cone shape or more the dynamics of the thrust chambers design?
The way it exhausts.
Exhausts out is
what you do is you worry about how it exhausts out if they interfere with each other.
So each engine probably doesn't have the same duplicate exhaust chamber. They would be tailored for its location and all of that, right?
Yeah. When I come back and tell you about the Aerospike engine.
Yeah, he's going to talk about the Aerospike.
It's a whole other discussion.
Yeah.
But that's about how nozzles work.
I've got an X-33 about this big we'll bring in for it.
Okay, yeah, but
Yeah, from Boeing. Yeah.
But yeah, so that's right. It's a lot more thrust than a Saturn V, or a little bit more thrust than Saturn V. Maybe what is it? 10 million pounds?
Yeah, they said 9 million,
Was it
something
9?
like that, right,
Yeah.
Marty?
So that's a bigger number, but it's divided by 33 rather than divided by 5.
Great, everybody. Oh, he said Jim McDade says he remembers Rolling Rumbles and a very hearing it rising and falling from the distances there.
Oh, in Huntsville?
Yeah, in Huntsville.
Well,
there.
we tell them that was the sound of freedom.
The sound of freedom.
That's what
yes,
that was.
That's right. It's like exactly when you smell a factory burning something, they say that's money in the air.
Yeah, money in the air.
There's another shot we'll never ever see again, though. We're going to have Artemis 2 rollout. To remind everybody, Kevin, have you heard the word on the Artemis 2 rollout? Marty over on our USAC family microphone has heard the rollout.
Yeah, I think that they've had it planned, and I guess they're talking about launching the first quarter of
Marty, when are they talking about rolling Artemis 2 out to the pad?
As of this morning, rollout is still scheduled for Saturday, this weekend.
This Saturday.
Yep.
Oh,
Yeah.
I thought it was even going to be Sunday, but this Saturday rollout.
I mean,
You're
obviously-
you're going to go out there and see it, right?
So it'll be 60 days out the pad, roughly.
You would think it should take 6 to 8 weeks, but they keep talking about 2 weeks. So I don't know.
Talk about a BHAG.
Yeah,
No,
BHAG.
well,
Big, hairy, audacious goal is
Yeah,
what
so,
BHAG is. I'm going to remember that. Big, hairy, audacious goal.
that's an old
Yeah,
rocket type
there's
saying.
going to be some valve on something,
Mhm.
hose. It's
But
not going to be
I
right.
still talk to some of the guys who are working the SSME, now called the RS-25.
Yeah,
They're very active with that, and they're very proud of it. The engines have been on the vehicle for a long time, and the engines are ready to go. But again, this is the first flow, and they're learning a lot.
yeah.
Just like everyone, they're learning. A friend of mine, Darvin, is telling me that they're having trouble figuring out how to close out the aft. And I mean, it's something that we had done pretty easily, and use common sense on the shuttle program. But
Close out the aft.
close out the aft. How
of the
to get platforms in there so you can work and inspect at the same time, remove the platforms without dinging something. There's a lot of damage that happens in the wear
before
and tear.
it leaves the
Yeah, so it's like stepping backwards very carefully, taking everything with you,
Mhm.
and doing inspections, and then doing tests to make sure everything is as it should be. So anyway, it's their first time, and so I would expect a little bit more than 14 days at the pad.
Yeah, really. Yeah, I keep seeing people on social media say February 6th. I'm going to be
Yeah.
there.
Well, I'm
which
rooting
is
for him. I'm rooting for him, but
yeah, absolutely. But it is Artemis fever has hit the coast,
mhm.
and it rolling out Saturday. Hope NASA channel does that live, but Marty will be out there, take some pictures, and show it to us on Monday out there. I know Artemis 1 was out there. It launched in November. They had it out there in like July. They brought it in for a hurricane.
I went out
Took it
there.
back out there, right?
We went out there a couple times for the scrubs, and it's very frustrating,
Yeah.
especially because it was a QD. But yeah,
QD.
a quick disconnect that was holding up the launch. I think it caused a couple of the launch
Oh,
scrubs.
quick disconnect.
A quick disconnect to the fuel system,
That August morning,
which is
was
something
just
we had
unbelievable.
figured out on the shuttle a long time ago. But they're learning. They're
Yeah.
learning.
Yeah. So, well, to that question pops in my head. The Artemis generation doesn't rely on the legacy companies much for solving problems. In other words, you could maybe be on a phone with somebody and give them an insight of what they need,
They don't want to
but
hear
they
it.
don't call you.
No, they don't want to hear it. I think they had the philosophy.
Explain that to the
Oh,
viewers out there that don't live here.
I'm not going to explain it for two reasons. One is I don't understand it and I can't explain it.
Okay.
When we were working SSME, we sat at the feet of the F-1 people to learn the mistakes, because the same mistakes are made by everyone. I mean, closeout's closeout.
Yeah.
And they could probably have learned from us. They certainly could have learned from us on the QD. But I don't know the details of that. I just know that they had QD problems, and they had
Quick
leakage to it.
disconnect on the
My tire, I put
vehicles.
air in my
Lot.
tires the other day, and that was just a QD. That's not too unlike, a fluid QD.
Okay. That's
So anyway,
interesting. Yeah,
but
I've heard a lot of
anyways,
stories from people that work out there that they're working on a problem and something's not getting moved and on in the flow that you said the flow is the flow of all of the steps that have to be done in order, right, to achieve a great launch.
well, I'm rooting for him,
And
but
they finally they did pick up the phone and call a shuttle person after 3 months of trying to figure this problem out, and within 2 days the problem was solved and they were back on track. And I really don't understand it, but that's the way of the world today. Okay.
Yeah, but Mark,
Yeah.
it's not the way of the world today. It's the way of the world for a long time now. It's the same thing going back to Gemini and Apollo days.
Uh-huh.
Gemini people say this is the way we did it back in Gemini, and depending on the department and what the problem was, well, that's not the way we're doing it today.
yeah.
So it happens. It just depends on the department and
hmm
what they're willing to learn from past experience.
Yeah. I think there used to be a saying we had early in my career, it was not invented here. They would say, well, we're going to, you did it, but we're going to invent it, reinvent it ourselves. And so, but you got to love them. And again, that's how they learn. And
It's just like Elon Musk lunar lander.
yeah.
Total reinvention of what worked in the past.
But one thing is, but you can use the same features. You don't have to reinvent every wheel of that complex
Tell
system.
that to Elon.
Yeah. But Elon, there's also Elon doesn't have a NASA oversight, which frees him up quite a bit. And so that's one of the reasons why he's been so effective. But we're getting far afield here.
Well, it's great conversation here for everybody listening today that watches our show to hear the banter back between two space workers about different generations. Do they rely on the other generations? No, they don't. And it's really weird in a way that I would want to know. I learned from my photography chops from my peers, but some people didn't want to share their secrets,
Yeah, but
type of stuff.
what you want to do is maybe you could ignore their advice, but at least hear their advice and see if there's something they can glom from that and maybe learn a step. But anyway, we're speaking out of school.
Yeah,
That's their program, and we wish them well.
We certainly do, and they've done well. The track record proves itself there.
Well, what do you mean track record?
Pardon me, I'm talking about the Falcon 9.
Oh, I was talking Artemis.
Oh, Artemis. No.
They're
What
1 for
track
1.
record?
It's not much. It's 1 for
1
1.
for 1, and 3 years later, we're waiting on another launch here. Okay.
Yeah, but Elon he's got as an engine guy.
The Artemis situation there. You and I know a lot of people that have some strong opinions about it that won't voice them, but it's not the NASA way. The new Artemis NASA way that got us to the moon. So got some good comments there. Jim McDade points out that the SRBs are motors and not engines.
That's correct. They're solid rocket motors.
Mm-hmm.
Yeah.
And not the.
I have to interrupt.
And he mentions the 4-chambered Russian engines.
Yeah, the RD,
a lot.
The RD-171 and the RD-180 are big engines. In fact, the RD-171 is the second largest engine ever produced.
Okay. And those were just the last ones used on a ULA launches?
Oh, no, I'm talking about the 171. That was used on the Zenit rockets.
Okay.
And I don't think that they're making them anymore. But the RD-180 you're talking about,
gotcha,
which is probably around the 4th or 5th most powerful engine ever built, and that was used on the Atlas. It's interesting because they were both made in Ukraine, and when Ukraine separated from the Soviet Union back in early 2000s, all those engines became available, and so a lot of smart people at ULA and Pratt Whitney went over and bought them by the warehouse.
Yeah, they didn't buy them from the Russians; they bought them from the Ukrainians who
and
built
so that's
them.
how they were.
So that was
which is interesting.
The
war in Ukraine is right in that area, and that manufacturing facility is right on the front line of the war over there right now.
Huh.
I don't know if you need to, but you may want to explain the difference between a motor and an engine.
Let's do that. Solid rocket motors versus a liquid fueled engine.
My job title at Rocketdyne was a senior scientist, liquid propellant rocket scientist, senior scientist. And so liquid propellant folks call solid rocket motors fireworks.
Okay,
but
and
they
they
don't
are. They're,
appreciate.
I
They
call them
don't.
pop bottle
They,
rockets.
they don't appreciate that. But the solid rocket motors put out a lot, and there's some advantages to them. The trouble is once you light them, you're going somewhere. Whether you like it or not, you're going somewhere. But there's disadvantages.
You
But
can't turn them off.
but there's a lot of advantages to them also, especially for things like ICBMs. Things that have to be stored in the silo for a long time. Um, I mean, they're very dangerous. Of course, they haven't really caused a problem, but they have the potential. In fact, that's why we were all thrown out of the VAB a generation ago, because they computed that an inadvertent detonation of just one segment of an SRB motor would evacuate all the oxygen out of the VAB, which is a big building,
Right.
would evacuate all the oxygen out of that building in a matter of a dozen seconds. And so that's why they said we can't, even though the possibility of that is so remote, the effects of that would be so catastrophic that everybody had to be moved out of the VAB just because of that. So there are some downsides to it, but it's very storable.
I mean, you had offices in the VA.
Oh yeah, everyone's office. That VAB housed all the flight hardware and all the offices of this Apollo program.
Okay.
And there was a lot of people working that Apollo program. That building just absorbs people. If you've ever been in there, I mean, there are enough offices for 14,000 people in there.
Really? I hadn't
Not
thought
to
of it
mention
that
the
way.
hardware.
14,000 people. Yeah,
Yeah,
and
so
then the
it's a-
hardware in there. Wow.
That was pretty big.
It
other-
is big. There's no doubt about that.
But the liquid propellants, you can't store them. They're a little volatile by themselves also. So I guess a solid rocket and a liquid rocket person probably could, over a beer, have quite an interesting discussion. But
Y'all got any questions for Kevin Hoshstrasser? I am happy to have him on our show again. He had a popular show in the SSME. Here is a beautiful 3D printed model there. Somebody asked, well, why is it silver? Is it silver thread? Is it paint?
it's actually a long name of a plastic, but it's also the same plastic that you find on a weed eater.
A
You know,
weed
the-
eater.
The
Okay.
weed eater string.
Yep.
That's basically the same stuff, and it's fed into a little printer.
Okay.
And
What'd you call this little section here?
well, this is the turbine exhaust volute.
Volute.
The volute. Now, we're getting off script here a little bit, but as a 3D designer, this was the toughest piece I've ever designed,
Oh, okay.
because you can see the changing geometry. It's shrinking in size,
yeah.
and it's rotating around, and the software
And it's not
packages-
at a right angle with the rest
No,
of
you
the
can
chamber.
see
It's a
it's-
volute.
I found it to be the most challenging design I have ever done, and I'm kind of embarrassed to tell people that that's the last thing I was able to complete on it, and I must have spent 9 months trying to figure this out, why I was designing everything else in its place.
Wow.
So it's very difficult for me to design, but that's the well, I'll go through this
You
piece
have
by
some
piece.
3D printers there that
Yeah. But what I found was 3D printing. There's several software packages, but if you own your own equipment, you're limited, to the specifications of that. And so if you're just a hobbyist, you really can't afford a very expensive machine to do it. And the other problem I found when I had my own machine was that, the inkjet, it just prints it just a dot at a time, and that little jet gets clogged, and you're always cleaning it out, and you always have to calibrate it. And so what I did was I found a print shop with very expensive world-class machines that will print this on a space available basis for pennies on the part. For instance, and since I'm a Rocketdyne guy, I think of this not as one engine. This is not printed as one piece. I print this as different LRU components that I could replace. So what I do is I actually print this out. There's a lab at the University of Oregon, or Oregon State University, that in their spare time they'll print these pieces for me. And typically, even if they're busy, it's not a 2-week turnaround. And so they do it much cheaper than I can do
Very
it.
good. Marty's got a question on our UCI family microphone.
Yeah, Michael Bruno was asking, has there ever been an SRB that can be turned off or a design for one?
Yes, that's a very good question because they're just coming out. Well, I guess it really is a solid propellant, but what it is a solid propellant that doesn't include its own oxidizer, like SRBs, like the shuttle SRBs and typical propellants do. They infuse the oxidizer into the grain. That's what they call it, the grain of it, the rubber piece. But there's a company just down the street called Via. And of course, I think I saw where you had Via gentlemen on TV.
We've had about 6 of their little engineers, and we
yeah.
had Kevin Loudermilk, the
Mhm.
CEO. You know Kevin,
Well, I don't know him,
president,
but
but
I actually got a tour of Via
Okay.
a year ago or so,
yeah,
and they gave us a tour. We met the team there, and what they do is they actually have pebbles of plastic that serves as the fuel, and what they do is they just introduce the oxidizer to it, and it forms a thrust. It actually burns, and if they want to shut it off, they just stop the oxygen flow.
hmm
They
So
can
that's-
throttle it also.
And they can throttle it
Right.
that way. And so the answer to that question is it's called the hybrid, and Via makes it, and I think there's several other folks who are getting into the business, but Via is probably I guess they're kind of leading the pack on this hybrid solid propellant, which is very interesting. It's so because one, it's very storable too.
yeah.
Now-
We got it in our. They gave us a rocket is in our conference room.
Mhm.
They're early plastic in there.
But
It's
I-
inert. That doesn't have any hazard.
And all you got to do is introduce oxygen, and it'll burn. But
And
it's a solid.
one hell of an igniter too. The igniter really needs to put the torch to them, so to
Mhm.
speak. And
But
they got someone that invented one.
That's an
there.
interesting engine.
Yeah, sure it is. Via Space. Look that up there. Great question there on there. And if you got another question for Kevin, we're winding up here by looking at some of the legacy pictures of the Saturn V rocket, the beautiful launch there.
Well,
That could
I've
be
got
a Tom Usiak's launch there. I know that's Tommy's picture. That good friend of our museum. We've got their Hasselblad remote camera system
hmm
on a display here. And I didn't throw the color one in there, but I love looking at this picture. These pictures taken downrange through big telephoto lens, just showing you the structure, the flame coming out of there.
hmm
Is there something that the trained eye sees in that, like you, that you can explain to us?
But see, this is a story for when I come back and tell you about the Aerospike engine,
Okay.
and maybe I'll ruin it right here.
No.
Before we get away from F1 and talk about the Aerospike, about the same time in the 60s, that same advanced research group and the development engineer group got together, and they did things like this in BHAG kind of way. They said, what was the perfect size nozzle? What limits? Why do you pick nozzles? And at the time, there was math that proved it, but rocket science was an art, not a science in those days. They would try something out if it worked, and they realized that if you had a high pressure, you were at sea level, a longer nozzle worked better, or I'm sorry, a shorter nozzle worked better. But when you got at altitude, when the atmospheric pressure was lower, longer nozzles were working. And so they said, what is the limiting factor, and what's a good size for a nozzle? So they got in research, and they determined with math and with trial and error that the perfect nozzle is tuned at an altitude, meaning an atmospheric pressure. And the perfect nozzle is when the atmospheric pressure at that altitude exactly equals the pressure of the expanding gases at the exit plane. So that's why you see, like you have an RL10 around here, right? Remember that has an extension on it.
Mm-hmm.
So it's good at
Atlas engine.
Well, they have extenders. So at sea level, it's a shorter nozzle, but as it gets up in orbit, they put an extender on it to make it a long nozzle. So there is a way to say what you want to tune the engine for, and you tune it for a specific altitude. SSME was tuned at about halfway up. It wasn't perfect at sea level, but it wasn't perfect at BECO when it was high, but through the main thrust, that's where it was most efficient. And so this team said, what's the perfect way to do this? And it's a long story, but the short story is they found out that if you turned a nozzle inside out, instead of having it this way, it went this way.
Yeah.
And the thrusters just impinged against the wall that reduced rather than expanded. If it reduced, that one side was left to atmospheric pressure and the other side was able to bounce off the wall and give you thrust. And you also could use atmospheric pressure, it also gave you thrust. And so the aerospike engine was designed to always be the most efficient at that altitude. Now, if you look at this picture, first of all, do you have a picture of an F-1 burning just at liftoff? You see, in fact, I think you have
Got a
one there,
close-up
how
there.
it's very tight and it's moving fast, that it's overpressured there and the
Uh-huh.
flow goes straight down. But go back to the other picture, you can see when it gets to altitude, the atmospheric pressure is less, and you can see the flame as soon as it gets to the exit nozzle, it flares out.
Uh-huh.
And that means it's not running as efficiently as it could. But again, you have to make a design sacrifice to decide what you want to tune your engine to. And so the trained eye looks at that and says that nozzle is way too short for that altitude to be running.
I
But
gotcha.
so that's what you see there, and that's why next time you see a rocket engine, if you see it, the nozzle, the exhaust coming straight down and maybe very tight, it means the nozzle's probably, a little bit too long for that altitude. And if you see it flare out, you'll be
Mhm.
it's a little bit
Well, we'll look
too.
forward to having
Yeah.
Kevin back and talk about the
But
aerospike
that's
engine there.
that's the real secret behind the
Yes,
aerospike
there
engine
you
that
go.
Rocketdyne made.
All that from just one picture there. Marty,
Yeah,
got a
we have
question?
a question from DKS 13827. Did you all hear about Mike Griffin say our next moon landing needs to be much more simple, like an Apollo landing, which is what I alluded to a few minutes ago?
If I was designing a program, I would probably follow closer to the Apollo program.
That's where
And Mike Griffin also put out a paper that it was a long paper, but he presented it to Congress and about the steps you need to take and the risk at every step to do it this new fashioned way, like moving propellants in orbit in zero G. I'm sure smart people can solve that problem, but it hasn't been solved, even tried yet.
We've transferred a teacup full, a coffee
But
cup
it's
full,
you know
if
so
that,
it's
and
so
they have to do thousands of gallons for that
in theory
starship.
they say they can do it, but in practice I'd like to see them get that technology down. But they also have a bunch of rocket launches that support this. Rocket launches to get gas to low Earth orbit, rocket launches to get to lunar orbit. And all the rockets, the stepping stones to getting there will require, and to this day, they don't know how many launches it will require to do this.
Yeah,
And here they're already talking about we're going to the moon, but they don't know how yet. And
yeah.
so if you say there's a 98% chance of success at every step, and even transferring the propellant in orbit, which we don't know how to do, if we say they'll figure it out, the 98% chance, you multiply that 2%, it adds up. And by the time you get to the actual probability of the safety factor, it means it's probably not a very safe way to do it. And that's what Mike Griffin, his paper was when he presented to Congress.
Mhm.
It didn't get a lot of press because Mike Griffin was kind of seen by NASA as someone who was critical, and so they kind of downplayed it. But he brought up some good points, and I haven't seen anybody rebut those points yet.
Former NASA Administrator Mike Griffin, a very smart man, and he did outline that. I shared some of that at some time, but yeah.
Maybe Marty remembers when we'd sit through the FRR meetings. People would say, "Oh, but with all this." Mike Griffin had a saying. He would say, "Who needs sleep? You can sleep when you're dead." And he expected us to work 24/7.
Huh.
And he said, but that was his famous saying. And I don't know how philosophy in life, but you can sleep when you're dead. Get to work.
Get to work, yes. He's smart, and other people tell me he's not afraid to let you know how smart he is about things. But he did present an Artemis rebuttal with a plan, very, very well laid out. You can find that in social world out there by Googling Mike Griffin and Artemis on there. So almost at the end here. Really always enjoy Kevin here. This is some pieces and parts brought up from the Atlantic Ocean of Bezos's group brought up the Apollo 11, right? So what are we
Well,
looking at there?
I have a present for both of you, for you and Marty. I was going to show this to you and give you one, and don't change pictures.
Okay.
I was going to give you one and ask you if you know what this is,
Ah,
and if you knew you were a real rocket scientist. I told you not to bring it up, and you brought it up.
yeah, sorry.
Okay.
Yeah, okay.
So on Saturday morning, I was telling Marty, on Saturday mornings I reserve my time to play with my hobby, and I was playing with this, and so I designed a F-1 faceplate, and I use it as a coaster and as a Christmas ornament. And it's my favorite one. And I thought I would come here and I'd say, if you know what this is, you know you're a rocket scientist. But
I'm not sure I would have known what it was. Marty, how about you?
So this is so you could use it as a coaster, and in December you hook it on your Christmas tree.
Oh, thank you.
It's a 1 to
Kevin.
10 scale, so that tells you how big this faceplate is for the injector. And since we're out of time, I don't have time to go into the interesting story behind the baffles on this.
This is where the fuel
And oxidizer mix
mix.
right here.
Okay.
Right about here. This is where the fuel and oxidizer mix. And so I bought one for each of you if you had answered the question. But, you ruined it. There it is right there. This is a F-1 faceplate with baffles. And Lee Solid was a big part of designing this, because I understand Lee, when they were Lee worked a lot on the Atlas program, the MA5 engine that Rocketdyne made for the Atlas. And they had combustion instability, and they solved it by building these baffles. And so when they had the same instability on the F-1, they went to the same baffle, and this solved the problem immediately.
Wow.
Combustion instability was the number one problem we had developing the F-1. We blew up 3 engines because of combustion instability, and they actually stood down for a year on testing until they solved this problem.
Huh.
And the interesting part about this also is that this was considered secret baffles to stop instability, and so it really wasn't well known. And then during the Apollo program, when Northrop, who were in charge of building the engine that took them off the moon, they wanted that had to be 100% reliable. It had to be extremely simple, and they had combustion instability. And NASA knew about Rocketdyne's little secret about how to do that, but I don't think it got to Northrop because it was a proprietary product kind of thing. And so Rocketdyne actually won a contract to actually be a subcontractor to Grumman at the time, not Northrop Grumman, but Grumman at the time, to help them solve their combustion instability on their SN engine. And it was something as simple as this. And so Rocketdyne got a contract. I think Lee Solid was a part of that team and went over there and they said, put some baffles in, here's how you do it, here's how you cool them, and combustion instability goes away.
So though I've ruined your present, can we still?
You can still have it, yes,
Thank you
yes.
so
And
much.
think of F1s every time you put your coffee cup or your.
It's going to go right here on the set of Stay Curious. Mine
It's
is.
also good for a 12-ounce Budweiser.
There you go. Or a
There you
big
go.
mug there. Exactly there. Thank
So that's
you,
what I do
Kevin.
on Saturday mornings.
That's awesome. What are these parts brought up from the ocean?
This is
there?
part of what Lee Solid was working on, like you talked about. These are the parts that came out of the ocean for Jeff Bezos. What you're seeing there is this. Well, you can see it. It's this upper part of this nozzle.
Gotcha.
And this combustion chamber upper part, and you can see where the ducts have been pulled away. These valves have been pulled away, and you can see the inlets to it.
Yes.
The LOX dome to the far left, and the fuel input, the fuel dome, is the second one in.
How these have been obviously
Totally
very
mangled, yeah.
but they've been
Oh, you can see the heat. The upper right was the heat exchanger. This part right here.
okay.
You see this, and this is the turbine exhaust area.
One engine off the Saturn V that sent Apollo 11 to the moon, and where's that housed at now? I don't know.
That was a good question. I mean, I believe it's his private property, but I think that he has got it displayed somewhere, and I really don't know where he's got it displayed.
And I know that the Cosmosphere in Kansas got a big ring or something off of it. I was there when that was uncrated.
Oh, really?
Years ago, about 8 years ago. Wanted to just wait. There's a good surprise there. Power to go. And there is Eric Baker. Above Eric's head to the left is your SSME engine And I found a poster of the flow and
yeah, it's
everything
nice,
on
yeah.
there that looks real good. You have to go back there and check that out. And how can we talk about the engines without talking about the master uh, Paul Callie's painting called Power to Go, a play on his Atlas engines, Power. This is 2 stories at a wall of 2 stories at the U.S. Space and Rocket Center in Huntsville.
That's a Saturn V?
Yes, yeah,
Okay.
that's Saturn V lifting off there, called Power to Go. Major work that Chris Callie's father did, Chris being a friend of ours here. And just to get you perspective, there's those engines in the background there at the Space Center there. So, uh, Kevin, thank you so much for taking your time and to do this, and very, very well done. We've got RG Jubilee watched here from Merritt Island, Mosley Park. Watch today Steve Jokums, Keith Sewell, Tom Usiak, Dave Stange is watching with Mia and Nick, his grandkids, and they're probably playing with the Saturn V rocket as we speak there up in Michigan. Ophelia Sauterelle in Paris, she's in Normandy, France when we last caught up with her. Dean Babcock's up in Illinois. Tom Celentano in Connecticut. Ralph Palmer is in Australia. Mark Thell. Carlton Bailey, hope you're feeling better, Carlton. Mitch Rothman he's got a Facebook page called NASA Man Space and talks a lot about Mercury, Gemini, and Apollo. Shares a lot of pictures there. Doug Forrest is in Los Angeles in the business there as a artist. Cliff Watson is in Pomona, Australia. Cliffy, hope you enjoyed this. Jim Haas is watching. So you got one of your family members on there.
I have a brother named Jim, but I don't think that's him.
Okay. Gary Gerald's watching. He's our Vidalia onion farmer in Georgia. Jim McDade, thanks for your contribution there from the Rocket Center. Jessie Q, my daughter, and my granddaughters Macy and McKinley watching today. Michael Bruno is down in Miami, and DKS13827 is watching, and as is Set It Up and Blow It Up. Marty, thank you for writing down everybody's names here on our Facebook page or our YouTube channel today. And one of our number one fans there, Steve Jokum, says outstanding show, as does Keith Sewell, our astronomer up there. And he thinks that those engines are at the Museum of Flight in Seattle, which is Bezos's home.
Oh, really? Okay.
Museum up there.
Well, tell him thank you for that. I didn't know that.
Thanks for sharing that.
I just thought he left them in his garage.
And DKS is in Arizona. Yeah, just leaves him in his garage and waiting for his wife to say, "Get that stuff out of here. You need to put it in your museum, Mayor."
Hey, Mark, talk about Steve Holcomb. Kevin, Steve is the one who designed this 3D.
Oh yeah, bring that over.
Yeah.
Since we're
You mind
talking
commenting on it?
Yeah, so Marty showed me this interesting.
Steve
looks like it's a
Jokums.
1:24 or 1 to, and that's expertly done. It's a low res, but the nozzle looks immaculately accurate. And I don't know how he did it. I got into modeling rockets, whole rockets, and decals is something I'm struggling with. But this gentleman has figured out how to make perfect decals that are exactly accurate to where they're located and what they say.
He has a business called Lake County Spaceport up in Illinois.
And Marty and I both appreciate the fact that you put a controller in there, because that's something Marty and I used to work on.
The controller right there. Steve Jokums, thank you so much. What a great, Marty loves it over on his desk. Yeah, it is. It's very detailed. And I figured, good, that the decals are in the right spots.
It's a perfect nozzle.
Yeah.
Perfect nozzle.
It's gorgeous there. So, today, tomorrow's Wednesday, and we may talk about Spacecom in Orlando tomorrow. Efforting a guest to do on that. We'll see how that works out. But we're getting into a busy time of January, of course, and so with the honoring our heroes of Apollo 1, Challenger, and Columbia, and we always do it by respecting the families and honoring the wonderful astronauts with telling a little bit about their lives there. So you want to check us into that. And Kevin will be back and talk about the Vortex engine. Not the Vortex engine.
The Aerospike.
Aerospike. What's
And
the
the nuclear.
Vortex engine? Where'd that come
I
from?
don't know. And one of the other things I learned from Vince Willock was the nuclear engine that Rocketdyne made.
Ah, okay. Well, let's talk about that on our next trip too. Is nuclear the way to go? Anyway, so thank you so much again,
My
Kevin,
pleasure.
for all
Good to
you
see
do.
you guys.
Thanks for the coasters here, and thank you all for watching today. Marty, a great job on Streamlabs. Anything else to button up over there?
No, it looks like we're buttoned up.
All right. Well, I'm going to get buttoned up and go see Winston Scott play his trumpet over there at the Italian American Club tonight with Joel's Jazz Cats. So, always a treat to do that and relax and maybe get you and Linda or
Lisa. Lisa.
Lisa. Well, I say Linda,
Linda.
for. I had Linda pop in my head from the lunch there. Lisa Malone is this gentleman's wife, and she was the public affairs officer next to
You have us.
Hugh Harris for many years, as I'm flipping out here. And we honor Hugh quite a bit here on our show from time to time. And Lisa does a great job of keeping all those legacy groups together there. She's got her group of PAO people, and we enjoy getting together. And Kevin shows up once in a while there too, and has a good seafood lunch there. So thank you all for watching. Until tomorrow, I'm Mark Marquette saying we appreciate everybody's support, and I can't wait to see you again to bridge the space between us. Thanks for watching.